So, in the last class, we gave a dynamic algorithm for the decremental single source shortest path problem. And recall that in this problem, we are asked to design a dynamic data structure that supports the following operations. It takes as input a graph with n nodes and m edges and does some pre-processing, and then it can handle the update operations which ask to delete an edge from the graph, and it can also answer a query where the query is what is the distance from a node V to the source node S. This source node S is also given as part of the input while pre-processing. Okay. So, the obvious and this is decremental because only edge deletions are allowed. If both insertions and deletions were allowed, we would have called it fully dynamic. So, we presented this data structure called event Shiloh tree. It basically maintains a breadth first search tree rooted at S, and its query time is constant and its total update time over all the m edge deletions is mn. So, since there are m edge deletions, the amortized update time is order n. Okay. And of course, the pre-processing time, okay, because it just started with a BFS tree. So, now this class we will consider a more general problem, decremental all pairs shortest path. So, the name suggests itself what the problem is to do. So, decremental all pairs shortest path. The pre-processing step remains the same, the update step remains the same, only the query changes. Now, there is no source node. So, the query is in the current graph. Okay. And we will give the following result. We will give a data structure with the following properties. With order log n, approximation 1 plus epsilon, total update time order m n log square n, and is also going to be the same. Yeah. Okay. So, fix any small constant epsilon. Think of epsilon to be some very small value. Epsilon, I mean that it will not report the exact distance, but rather it will report a value lambda with the following property, that the distance between u and v is at least lambda and at most 1 plus epsilon times lambda. So, it will return a 1 plus epsilon approximation to the distance, and this is the total update time, total pre-processing time, and the query log n. So, now before proceeding any further, what is the trivial bound we can get, say in terms of total update? bound is you just run n eventual trees from each node in the graph, right. Then when you are asked the distance between u and v, just look at the eventual tree rooted at u, see what is its distance from v and report that distance. So, the trivial, and please stop me if you do not follow something. Okay. For that, be order mn square. So, the result that stated, it improves this mn square to mn log square n. Okay. The next observation is, note that this log n terms, this log square n or any polylog n term is much smaller than the polynomial terms here, okay, mn. So, we will often use this notation. Are you familiar with this tilde notation, O tilde of mn? So, this O tilde notation hides all polylog n factors, and the understanding being that they are insignificant compared to this mn term. Okay. So, the preprocessing time is also O tilde of mn, and the query time is O tilde 1. Okay. So, now what is the best you can do for the static problem, all pairs shortest path? The best known combinatorial algorithm for the static problem itself takes mn time, because you need to run m Dijkstra's algorithm from each source, okay, from each node. Here, because if you are using fast matrix multiplication and some algebraic techniques, you can get something better, slightly better, but the best known combinatorial algorithm takes this much time. Okay. So, now, and this algorithm itself will also be combinatorial. So, now can we ever expect to beat the total update time of mn here? Can we get less than mn update time for this problem? No, right, because the preprocessing time itself is also mn. So, if the preprocessing and the update times are less than mn, that means you have a better algorithm for the static problem itself. So, ignoring these polylog n factors, which are significantly small, this matches the running time of the best known static algorithm. So, this is in some sense optimal, conditioned on the fact that the static algorithm is optimal, which we could not say for the previous eventual tree algorithm, right, because there what is the best known static algorithm? It is just build one BFS tree that takes m time, whereas here the total update time was mn. Okay. Okay. And the paper is, let me just cite the paper here. Which has this result. It is dynamic approximate all pairs shortest path in undirected graphs by L T is weak 2004. In the paper you will see that they actually give constant query time, okay, but that requires a lot more work. In the class I am just going to present the log n query time, okay, to highlight the main ideas. Okay. So, main technique that we will use is the following. Okay, before we go to the main technique, let us just have one observation here. We showed how to maintain a BFS tree with total update time mn, but now suppose we modify the problem and you only need to maintain a BFS tree till depth h. Is the problem clear? So, just maintain the BFS tree, but the moment you see that a node is more than h distance away from the root, you just do not need to keep track of the node anymore, you can just ignore it. Okay. So, this is a BFS tree up till depth n, right, because in an undirected graph the maximum depth can be n, correct. So, stating first this, an eventual tree till depth h ticks. So, this will be an immediate corollary of the result presented in the last class. Why? Because recall our argument. What was our argument? That each time the algorithm is doing some work, the rank of an edge is increasing. What is the rank of an edge? It's simply the depth, sum of the depths of its two endpoints. And then we said that the maximum value of the rank can be 2n, because the maximum depth of a node can be n. Now, here we are saying that you just need to maintain the eventual tree till depth h. So, the maximum rank of an edge can be 2h. So, the total update time will become order mh. Is it clear? So, you can just go through the proof and see that it will be an obvious corollary. Okay. So, now the thing is, what we will do is as follows. We will maintain multiple eventual trees. So, basically, okay, this is the basic framework for the algorithm. Let me take a step back, just 1 second. Designate some nodes and maintain of some depth So, the naive approach would be every node is a center, and from every node you are maintaining an eventual tree of depth n. That is the naive approach, and that will give you a running time of mn square. But the trick would be, we will only pick some of these nodes as centers, and we will also vary the depth of the eventual trees maintained from these centers. Okay. So, these are the two flexibilities that the algorithm will have. And now, these centers and the depths of the eventual trees will be chosen in such a way, so that the total update time becomes tilde mn. However, if you are asked to return the distance between two nodes u and v, just as in the naive approach, you have to infer that distance from the eventual trees that are being maintained. Okay. Okay. Basically, what we will show is the following. Suppose there are two nodes u and v. can think of this diagram, and suppose they are roughly a distance d away from each other. Okay, say this distance is d. There will always be a center that is very close to one of the endpoints, say within distance epsilon d away from it. Here is a center C, epsilon d away from u. Now, since C is epsilon d away from u, what is this distance? One plus epsilon d. Okay. So, if we maintain an eventuality from C of depth order d, we should be able to reach V. So, when we are asked to find the distance between u and V, what we will do is, we will first quickly identify a center that is very close to V, close to u, and then probe the eventuality of that center, and then return the sum of these two distances, because the eventuality from C will have both u and V in it, right. So, we will just return the sum of the distance from C to u and C to V, and this will give 1 plus epsilon approximation. This is the main idea. So, two things we need to be careful about. One, we need to pick the centers in such a way so that this property is satisfied, that every node has some center close to it. And the second thing is that it just suffices to maintain an eventuality until depth use, and this will also improve the running time. Okay. Okay. Now, I will elaborate on this just in a while, but before going there, how many of you are familiar with Chernoff bounds? Because this will be a randomized algorithm and we will use Chernoff bounds. You are not? You are? Okay. So, is there anyone here who has not seen Chernoff bound before? Do I need to make a brief detour? No. Okay, good. So, to implement this, designate some nodes as centers, we will use a simple random strategy. So, the strategy is pick the centers randomly with some probability. Okay. And so, here if you just want to in two phrases, in a small phrase, highlight the main technique behind this result, he will say this just uses random sampling along with eventualities, and these eventualities in turn work because of the principle of monotonicity. And throughout the course, we will see multiple uses of random sampling in dynamic graph algorithms. Okay. Okay.
So signal is not coming from the receiver.
Oh. That's fine.
Actually, please take this. Yeah.
Check. Is it fine now? Did we miss anything?
No.
You didn't miss anything, right? Okay. Okay, so now let us delve into the details. I'll make two assumptions and I'll later on relax these two assumptions. The assumption 1 is there is only one query. What do I mean by that? You start with a graph of images and then it's a decremental setting. So, how many updates can there be? At most m updates, right? And how many queries can there be? After each update there can be n square different queries, because there are just n square different pairs of nodes. So, there can be overall mn square possible queries, but I am just assuming that you just go through a sequence of age deletions and there is just one query. Okay. And we will later on we will see that it really does not matter. I mean, even the general case can be solved easily. The second assumption we will make is on this query itself. So, note that this is the range of all possible distances, since it is an unweighted graph, right. That when the query comes u comma v, we know close to d, say between d and 4d. This 4 does not matter, just you can replace 4 with any arbitrary constant, okay, 10 or something, and this d is given to us. Now, you might ask why assumption 2 does not make the problem, does not it make the problem trivial, because we are given d and we know that the query will ask the distance between two nodes whose distance lie in this range, but it is still not trivial because we want a 1 plus epsilon approximation, right. If we just wanted a constant approximation, this problem would have been trivial. Okay. So, now we will just solve this problem and later on we will see how to extend this to the general case. Any questions? Okay. So, the algorithm is deceptively simple. Step 1, this is the pre-processing step. Pick each node as a center with probability C log n by epsilon from each maintain an even Shiloh tree Any question about the algorithm? This is just 2-line algorithms. Okay. In addition, you will need one data structure. The data structure will be, okay, so what is C? 1 second. C is just some large constant, 100, 200, 1000 that will go into the Chernoff bound. Okay, it's not significant. So, you will also need one data structure. The data structure is, let me say C star of V for every node V. This is a center within epsilon d distance away from, if there is any, we do not know for sure if there will be any. Okay. Now, first, what is the it will be expected update time, right? This is a randomized algorithm. Anyone? Yeah, because see, in expectation, how many centers will you pick? Each node becomes a center with probability this much. So, the expected number of centers is n times C log n by epsilon d. And from each center you are maintaining an eventually depth, this 4 plus epsilon is just a constant, right, until depth d. So, these are the number of centers and each eventually tree will cost this much time, right, md time. Now, we see that these two d cancels out and becomes order mn log n by epsilon. Okay. We have not taken care of one other thing, the data structure. How will you maintain this? This is just the cost for maintaining the eventually trees. In addition, I am saying that for each node v, you need to maintain a pointer that will point to a center, if any, which is close to v. You have to update this pointer, right, because the distances are changing, they are increasing. Anyone?
There are like at most n by C log n by epsilon d centers.
Mm-hmm.
So I mean the max distance is n. So
Mm-hmm.
there will be a center in at a distance at most nd by C log.
No, I do not get it. You need to have the center within epsilon d distance away, right? Okay. Yeah. Okay. So, okay, the solution is actually very simple. In the initial stage, during the pre-processing stage, suppose you just initialize these pointers. Okay. So, this is for every node v. Okay. Now, when will you need to update this pointer? Only when something changes in one of the eventually trees you are maintaining. If after an update step none of the eventually tree changes, trees change, then you do not need to update anything, right. So, the total cost of updating these pointers will be subsumed by the total cost of maintaining these eventually trees. So, it is as if you are just running the eventually trees algorithm and in deletion occurs, there are these many eventually trees, you go ahead and update of them. The pointer C star of v and try to update it. Is this fine? Any question? So, the total update time is going to be this much. Okay. And now the approximation ratio. Sorry, not the approximation ratio. First of all, we need to show that we can answer the query correctly with high probability. So, for this is the correctness proof. So, suppose the query comes and the query is u comma v. Okay. Suppose this is the query. The first claim is with high probability there is a center C such that the distance of this center from u is at most epsilon d. Now, since this is symmetric, you can just replace u by v, then also this will hold. Okay. But why is this the case? So, this is u, this is v. Now, just look at a ball around u of radius epsilon d. So, what is this ball? This just consists of all the nodes S such that its distance from u is at most epsilon d. Okay. What is the size of this ball? The size of this ball has to be at least epsilon d. Why? It is because we know that this path has distance roughly order d, the path from u to v. Okay. So, just pick the first epsilon d nodes in that path, they will belong in this ball. Otherwise, we could not be sure, right? If this guarantee was not there, maybe all the edges have been deleted and we are dealing with an empty graph, then this ball will only consist of u. But the fact that u and v are roughly d distance away from each other guarantees that the size of this ball is at most at least epsilon d. Okay. Now, each node in this ball is picked as a center with probability Cn log n over epsilon d. Is expected number of centers in this ball. What is this? There are at least, sorry, this is going to be at least. There are at least epsilon d many nodes, each is being picked as a center with probability C log n by epsilon d. So, this is at least C log n. Okay. And now you can apply Chernoff bound. Why? Because this expectation is at least C log n. And since so basically there are some indicator random variables, one corresponding to each node, and that random variable is turned on if this is a center and off if this is not a center. And what it says is that the sum of the expectations of these random variables is at least C log n. So, what is the, and these are independent, you have made them into centers independently. So, what is the probability that at least one of them will be turned on? This is just the probability that the sum is at least 1, sum of these random variables is at least 1, whereas the expectation is C log n, and hence the probability of this event occurring will be that number of centers in BU equal to 0, this is the probability. This will drop exponentially with respect to the expectation. So, this will be, I think, something like this. The exact term does not matter, C log n by some C log n. So, this entire thing will hold with high probability. Okay. So, the only thing you need to remember about Chernoff bound is that the moment you are considering sum of independent random variables and you want to bound the probability that this sum deviates too much from the expectation, you get high probability bound as long as the expectation is of the order of log n, because the probability of the bad event drops exponentially with the expectation. Okay. So, you can just work out the math here, that is not very important. Okay. So, we now know that when this query comes, with high probability there is a center close to it. So, let me erase this part. Lemma 3 is with high probability a 1 plus approximation answer to the query. Now, why is this the case? Again, just look at this picture. This is U, this is V. With high probability, there is a center very close to U, and this distance is epsilon d. Now, what is this distance? Say this distance is h. This is the actual distance. Okay. Now, we know for sure that h, distance between u comma v, is at most 4d. This is by assumption 2 on the other side of the board. So, what is going to be the distance between the center C and this node u? By triangle inequality, this is going to be at most h plus epsilon d. So, this is going to be 4 plus epsilon times t. So, this is V, please correct me. Okay. So, this node V is going to be part of the Eventualo tree from the center C, right, because the depth of the Eventualo tree rooted at C is at least 4 plus epsilon times C. Okay. So, this distance is going to be, you can check that this distance is going to be at most this. Okay. Now, how will you answer the query? When this query comes, you just pick any one node u and then just probe the data structure. So, recall that in this side, in the data structure, for u, you are maintaining the center that is within epsilon d distance away from u. So, you just probe the data structure to find this center C. Then in the Eventualo tree of C, you just ask what is the distance of u from C and what is the distance of v from C, add up these two distances and just return the answer. Okay. So, what is the query time? The query time here is constant. Okay. Now, let me erase this part. So far we have made two assumptions, we just need to get rid of them, right, assumption 1 and 2. So, let us first get rid of assumption 2. This distance, in which this distance will belong. So, dealing with assumption 2. What you do it is, just discretize this range 1 to n into order log n groups. So, group I will look like this. It starts at say 4 to the power I and it ends at 4 to the power I plus 1. So, since you are doubling this thing in powers of 4, there will only be order log n many groups. Okay. Then for each group I, run the algorithm which we did so far. Now, two things. One, what is the total update time and how do you answer the query? So, total update time. Let us just consider the update time for group I, then we can just sum over I, right. Let us say I equal to 0 to L. Okay. So, what is the update time for group I? You can just replace D here by 4 to the power I, that is it, right. So, for group I, recall the algorithm is pick each node as a center with probability C log n by epsilon times 4 to the power I, this probability changes. So, the expected number of centers is this, and from each center you are maintaining an Evenshilo tree of depth order of D, D was 4 to the power I here. So, this is the total update time for group I. And what is this? This thing cancels out. You see that this is nm log n, right. And how many groups are there? There are only log n groups. So, this total update time becomes as promised mn log square n by epsilon. Okay. Now, answering a query. So, this is a very standard trick in the sense that you just observe that the distances lie in a range that are polynomially bounded, and you observe that you can solve the restricted problem when the distances vary only by a constant factor. Then you can just discretize this range into log n groups and incur a log n factor more. in the running time. Okay. So, now answering the query. How will you answer the query? So, a query comes u comma v. You can go through each of these groups. There are only log n many groups, right? And from each group you can find a center that is close to u. So, basically you are looking at group I u comma v. Suppose you are looking at group I. So, you probe the data structure and you find a center C that is say within epsilon times 4 to the power I distance. Okay. And then you observe whether V is in the eventuality of C. If V is not in the eventuality of C, what will you conclude? That we must go to a higher group, right, because maybe this distance is basically roughly of the order of 4 to the power j, where j is much greater than I. Then of course you won't find V to be in the eventuality of C. Okay. So, basically you will just go through log n of these groups, each of these log n groups, and from each of these groups you will try to extract some answer. Okay. Now, some of these answers will be, I mean, for some of these groups you will not find any answer at all. You can of course discard these groups, but still there might be multiple groups which gives you some answer. It can happen. Which answer will you pick? Yeah, the answer coming from the smallest group. Why? Because suppose this distance is roughly of the order of 4 to the power k, where k is much smaller than I. Okay. Then when you are probing group I, so here we are at group I, so let us just erase this part. Okay. When we are probing group I, what can we observe? We can definitely, it is very much possible that C is epsilon 4 to the power I distance away from u, right? It does not prevent it from happening. But now the point is, since k is much smaller than I, this distance from u to C itself is much larger than the distance from u to V. So, this is say epsilon times 4 to the power I, right? And then you go to the eventuality of C and you see that okay, V is present of course, because its distance from C is of the order of 4 to the power I. But you sum up these two distances and you return something that is way off the mark. Any question? So, you just need to pick the group with the least index that gives you a valid answer. In one line, this is the thing, and hence the query time will be of the order of log n. Okay. So, now those of you who are familiar with some data structure tricks will observe immediately that you can just improve this query time to order log n. Why? Just do binary search on these log n groups. Since you want to find the group with the least index, You just don't need to go through them sequentially one after the other. You just do a binary search and this will drop to log n. Okay. But to get constant query time, you need to do something quite more complicated. It's called distance oracles, and I am not going there. But you can still bring it down to constant as well, the query time. Okay. So, now the last thing that remains is this, getting rid of assumption 1. So, just recall assumption 1 here. We just assumed till now that there is only one query that we are answering, but there can be polynomially many queries, right? How to deal with this? But this is going to be very simple, right? Because if you just fix one query, you get a correct answer with high probability, and now there are only polynomially many queries. So, you can just apply a union bound. So, one query fails with probability. So, a given query fails with probability, say at most 1 over n to the power c. So, there exists at most m n square many queries, right, and m can be at most n square. So, by union bound, some query fails with probability at most Now, if you just make C to be sufficiently large compared to n, this is still going to be a high probability event. Okay. So, you just say that this is. Now, here is one crucial thing. Although this is quite simple, I just wanted to isolate out assumption 1 for the following reason. Since we are in the decremental setting, and since m, the initial number of edges, can be at most n square, that is why we are getting this property that there can be at most polynomially many queries. But if we were in the fully dynamic setting, can we get this property? No, because there can be potentially as many updates and queries as you might wish for, right. So, if this was a fully dynamic setting, we would say that the guarantee of the algorithm holds for only polynomially many queries and updates. But for the decremental setting, we do not need to make this statement. Okay. But for the fully dynamic setting, if you give a randomized dynamic algorithm that is true for just polynomially many updates and queries, that is considered to be good enough. But still, you should just keep this in mind, the distinction between decremental and fully dynamic settings.
But we have to choose the probabilities.
Sorry?
We have to choose that C before we decide on the function.
Yes. So, basically you will say that okay, give me any t such that you are allowed to give n to the power t many updates and queries, then I can just prepare the algorithm in such a way that this will work for this.
So, the constant d that t comma 4t, that the only work for that is to make this order log n.
Yes.
There is no other.
No, you can just make it 2d, 10d, whatever you want. Okay. So, what is the takeaway message from this? One, you just saw an example of a problem for which the guarantee of a dynamic algorithm nearly matches the guarantee of the best known static algorithm. There is 1 plus epsilon approximation ratio, that is where it does not match, and the second one is that there are some additional log factors in the update times. which is worse. And the second thing is that you saw this technique of random sampling, and this is used in many different problems in dynamic graph algorithms, and we will see its use multiple times throughout the later half of the course. Okay. Okay, so let's stop for this week.